Good morning, everyone. Welcome to Concordia University's Fourth Space. Thanks for joining us for today's event, Large-Scale Energy Storage, Demand and Challenges. Now, these are industry, policy, and academic perspectives. We'd like to begin by acknowledging that Concordia University is located on unceded Indigenous lands here in Chichage, Montreal. And we respect the continued connections with the past, the present, and the future in our ongoing relationships with Indigenous and other peoples within the Montreal community. Here at Fourth Space, we work with our university community to help mobilize knowledge. We co-create daily activities that examine research questions, projects, things happening across the university. Now, we're running today's event as a live stream both to YouTube and via Zoom. So if you're joining us there, welcome. Any comments or questions, just add those into the chat. We'll do our best to read those out a little bit later. And those of you joining us here in the space, if you have any comments or questions later, that's wonderful. Just raise your hand. We'll run a microphone over to you so that everyone else can hear. Okay. It's very much my pleasure now to hand the microphone over to doctoral candidate in the Department of Chemical and Materials Engineering, as well as current Concordia public scholar, Maysam Maleki. So great to have you in.
Thank you. Thank you for the introduction. Good morning, everyone. Happy to see you all here. So today, as you mentioned, we are going to talk about the large-scale energy storage, demand and challenge. First, we will have the introductory presentation by me. I'm trying to keep it short, so we will have time for a presentation from our speakers. And then we will have the presentations, and at the end, we will have just a panel discussion for around 30 minutes. Okay? So just to start, let's focus on the bigger problem in the world. And climate change, global temperature, as you see here, the global temperature over the past few years increased, right? From 0.42 degrees centigrade to over 1 degree. And these are all temperature relative to averages in 1980s. Somebody might say 1 degree is nothing, right? But we are seeing the effects right now. Look at this graph. This is the amount of land burned by wildfire in 2023 in Canada, more than 16 million hectares, right? So this is not a problem for the future, it's happening right now. Climate change, greenhouse gas emission that we are all polluting every day, right? And most of the global greenhouse gas emission is coming from the energy, how we produce, how we use that, right? 75% of all the greenhouse gas emission globally is coming from the energy sector. In 2022, around 41 gigaton of carbon dioxide, right? So if we want to tackle the global warming, climate change, we have to do something about how we produce and how we use the energy, right? But before seeing how these global warming and carbon dioxide is going to the air, let's see how the energy demand is increasing over time. Since year 2000 to year 2023, we see more than 50% increase in the demand in energy, right? Mostly because of electrification, EVs, and AI is coming right now. So we are going to see more and more of energy demand. And at the same time, if we look at the energy mix, right now, most of this energy are coming from fossil fuels, unfortunately. Oil, coal, and natural gases. Oil, more than 30%, right? This is total energy supply in the world. Now let's look at the total energy supply in Canada. The situation is better. In Canada, we're producing our energy mostly with hydropower, more than 60%, right? This is a clean energy, that's nice, but this is also can be affected by the climate change. For example, in 2023, due to the low precipitation in Canada, the average, the reservoir volume of the hydropower decreased to lower than average. The situation was even worse in BC, so BC Hydro had to import power to meet the provincial demand, right? So we gotta do something about the climate change. It's not only Canada, it's around the world. And one of the ways to do that is to reach to net zero emission. Canada, like many countries around the world, put an ambitious target to be net zero by 2050, and that's not going to be reachable unless we are changing how we are producing and use the energy in the energy sector, right? So this is where renewable energy are coming to play. They will play a big role into the net zero emission. Talking about renewable adaptation during the past few years. Hydropower, you see the increase in the adaptation. Wind and solar cells. These days we can produce more and more power through solar and wind, mostly because of the advances in the solar panels and decrease in the cost. Right now, the cost of producing energy using solar panels decreased by more than 90%. And it became the most cheapest source of energy in many parts of the world, right? So they are making a lot of energy with solar, wind, and hydropower, but there is a big challenge here, right? And that challenge is the variability of the renewable energy. To really grasp what does it mean, the variability, let's look at the real data here, Quebec, on March 15, for example, right? These are real data coming from Hydro-Quebec. You see in the 12 a.m., there are not much of the power demand. As the day starts, we wake up, we want to go to work. The demand is increasing. And during the midday, after 7 a.m., you see a decrease in the demand that we need, right? And again, when we come back, it's night, the demand is increasing. So imagine that on March 15, it was a fully sunny day, right? It wasn't, but let's imagine. When we will have the opportunity to grab the most out of the sun, when would it be? It would be, it would be around 10, 1, 4 a.m., right? This is exactly where our demand is the lowest, right? So this is the problem with the renewable energy. They are available when we don't need them that much, right? And the situation is almost the same for wind. Wind is also really fluctuates. It's not predictable. Also, the maximum power that we can reach, we cannot predict that, right? So the question is how we can manage this. Renewable energy is variable, and we want to have the energy when we need them, right? So I want to pause here and put the variability of renewable energy aside. Let's focus a bit about the grid reliability. And for that, I want to show the data for the power outages, for example, in Nova Scotia. In 2024 alone, Nova Scotia experienced around 5,000 of power outages, disturbing homes, businesses, hospital, right? And mostly coming from causes like weather, high speeds, climate change, right? The snow, rain, around 41 days, that was the problem, that was the cause for the power outages. Fire, again, climate. Trees on line, around 36 days. Even lightning, right? These are causing the power outages. So variability, and also we want a grid that is reliable. We want energy all the time, right? If you remember, I showed you that the Energy demand has been increased over the past few years and is going to increase. AI, data centers, right? They're coming. For example, at 2024, the demand for data centers was around 460 terawatt hour and is expected to increase to around 1,000 terawatt hour at 2030, and at 2035 around 1,300 terawatt hour in the base case. And if the adaptation of AI and data centers is going to be higher than expected, according to the current policies, that's going to be around 1,700 terawatt hours. So we need a lot of energy. Maybe it's worth noting that energy demand of a modern data center is going to annually is going to be 100 megawatts, and this is equivalent to 350,000 of electric vehicle, right? This is a lot of energy that a modern data center would need, okay? So to wrap it up, energy demand is going to increase, and for net zero climate action, we need to address them with clean energy. Clean energy is variable, right? And electricity supply should be reliable. This is where large-scale energy storage will play a big role here, okay? It can act as a bridge gap. We can store the energy when it's available, for example, at 1 p.m. when we don't need that much of energy, and use it when we get home during the night, okay? So today we're going to talk about large-scale energy storage, and we're fortunate to have our speakers from different perspectives, industry, academia, and policy. And for the first presentation, it's going to be industry by Sonia. Thank you for being here. So Sonia has been working in the energy sector for over 25 years and has extensive experience in commercialization, project, and infrastructure deployment, strategic planning, and finance. Now, she's the president and CEO of Evlo Energy Storage. She started with Evlo in 2018 and has served as a CEO and CFO there. She has also held positions as treasurer and administrator with various production division, subsidiaries, and was a member of a plan-no committee. Please.
Hello, everyone in the studio, watching, Mesen. Thank you very much for having me today. I'm Sonia Saint-Arnaud, CEO at Evlo Energy Storage. For those who may not know Evlo, we are a proud Canadian provider of battery energy storage system, and we are a subsidiary of Hydro-Québec, North America's largest renewable energy producer. Over the last decade, we have brought the commercial phase of a deep expertise in LFP, lithium iron phosphate technology, backed by an advanced knowledge of power grid. Our team has designed 6 generations of product and deployed across Canada, USA, and France. I am happy to bring to the table today the industry and deployment perspective. I don't know if I need to wait the presentation because I have a beautiful image for you. Good. Good. You can see where our projects are presently in Canada, in USA, coast to coast, and in Europe, in France. Good. If we speak about large-scale storage and customer needs, so let me start with big picture with a few quick facts. And I want to thank Benchmark Mineral Intelligence for providing us with the following data. Large-scale storage is now a core part of modern electric grid around the world and is increasing its share in the global battery demand. Just looking BESS, we can observe an annual increase of more than 50% demand each year. And LFP, lithium iron phosphate, has confirmed its leadership. It gives long life, safe operation, and stable performance even with heavy cycling, with affordable commercial pricing. Not all regions are equal with this technology. China early has the most deployment and the largest pipeline, and the USA being second. Some other countries who are early adopters of BESS are Australia, UK, Chile, Saudi Arabia, to name a few. We can also notice that the average project size has increased every year to reach over 250 megawatt hour in 2025. And project size continue to grow. For example, in Ontario, we currently see large-scale projects in development or recently commissioned for more than 1,000 megawatt hour, 1 gigawatt hour each. The two biggest projects are near 2,000 megawatt hour each. Here we can see our parent project, 20 megawatt hour. When we look, the new one project in Ontario is 100 times more of this size of the project. You can imagine it's really big. If we wonder what BESS is used for, yes, they are paired with renewable in the last year and will continue to be. We can see two behind-the-meter usage, but the stand-alone BESS are the most popular category. Why? Because they can be paired with renewable for multiple sites and deliver multiple value streams from peak shaving to grid services using the same asset, the same BESS standalone. It is important to understand where and why you are doing to use your BESS in order to get the right solution: generation, transmission, distribution level, or behind the meter. If we speak about energy storage is used for, yes, it's sure, like introduced by Mason, it's bring more renewable energy. Why? Battery storage is the simple answer to the fact that renewable of intermittent nature, and it is important to firm up this energy. Firm capacity and energy on demand. We can use BESS for support peak demand and peak shaving too. One of the biggest challenges for any grid is having enough capacity to meet demand during peak hours. BESS also prevent the activation of expensive peaker plant, and it can be done behind the meter and front the meter. Energy arbitrage, other one usage. BESS can help utility with most saving and can provide commercial operator with new revenue stream. BESS charge during low cost and low demand periods and discharge when price and demand are high. Improve grid stability and services quality. BESS can inject and absorb power within milliseconds to keep grid frequency stable, like our project in France, Project Tonnerre. We can think of notions like virtual inertia, fast frequency response, and voltage support services that become more important as conventional synchronous generator are displayed by renewable. Grid forming, interesting concept. Unlike traditional grid following resource, grid forming storage does not simply react to the grid, it actively establishes and stabilizes grid voltage and frequency. And finally, backup power, microgrid support, remote community resiliency. As a generic term, storage can support critical load during outage caused by storm, extreme weather, or during planned grid maintenance, like our parent project. In remote or isolated grid, best reduce diesel consumption and allow communities to integrate more renewable energy. It is a strategy used in Quebec to help lower greenhouse gas emission in remote community, Kuujjuarapik project like example. Typical energy storage customer come from three main groups. First, utility, and the second, independent power producer, and third, large industrial customer. From the meter, some utility will choose to be the owner of the asset, another one will choose to do a PPA, power purchase agreement, with independent power producer to have the best services. Typical duration range of the best battery energy storage system. For large-scale storage, the most common duration today are between 2 and 4 hours, most probably because it is the best balance between the need and the cost of the technology. There is a growing trend for longer duration, between 6 and 8 hours, but it is remain a smaller market share for now, 6%. But the future will tell. Okay, if we speak about challenges, because it is the request for Mason, we have a lot of challenges. First, we will speak about scaling up and product development challenges. Battery storage only works at scale. Costs come down only when volume go up. Scale is critical, but difficult to achieve. To get competitive pricing, a company like Evlo needs enough volume, both from customers and to commit it to supplier. The challenge is that Evlo must commit a certain volume with key supplier, battery module, BMS, containers, converters, in order to start production, even before it was firm order covering the full volume from customer. Because each component has its own lead time, this element cannot move forward independently. This also implies how to balance design maturity with commercial commitment. On one hand, the sales team must offer the new generation product today that will be finalized and tested later. On the other hand, engineering and design team naturally need time to refine and optimize solution. In practice, we will to be confident with a minimum viable product to begin with, then trust the engineering team that they will finalize the development within the project timeline. Design team, manufacturing scale, supplier commitment, and project pipeline with early adopter all need to move forward in parallel. Other complexity in scaling up the mindset of engineering team. When designing and developing a product, engineers need to think beyond performance. They must consider how the product will be manufactured. The goal is to design not only a product that performs well for the application, but also one as simple as possible to manufacture, cost-effective, and robust for transportation and field operation. Another aspect is the speed of the product development. It is important not to fall in love with your product. Innovation moves very fast. At Evlo, we design a new generation every 12 to 18 months as key components improve rapidly. In 5 years, energy storage has evolved as much as solar did in 15 years. If we go to the installation challenges, this type of challenges integrator can face approaching the development phase are multiple, but let's group them today under 4 categories: hardware, software, project management, and geopolitical challenges. Hardware. Sure, procurement and supply chain is a challenge. The best industry depend on stable supply, battery, cell, transformer, power, electronic, and just one missing component can delay a whole project. The second challenge for hardware is logistic. As you can imagine, best weight several tons. You need a road that can support the load, the right vehicle, and specialized crane. We have also shipped our system across the Pacific Ocean to the Americas Samoa. It is a special challenge given the size and weight of battery energy storage system. If we speak about software, interesting subject too. EMS, Energy Management System, is the best brain. The energy management system must communicate with all software systems at the same time, with many software systems at the same time. The client SCADA, the BMS, the converter, and other site equipment like PV. Everything has to work together seamlessly. If one part of the system does not respond as expected, the overall performance of the BESS is affected. We can speak too about tests and criterion for acceptation from the utility. Talking about the grid and grid events, utilities are very focused on stability and control. The BESS system must support the grid, not create additional stress. To run normal operation, every BESS must speak the language and be compliant to the local grid. Our team need to plan and test for abnormal events during commissioning phase. The challenge is to establish the test plan and establish what metrics are we measuring and what acceptance level are we targeting. Otherwise, the test itself has not real value and we waste time in interpretation. Project management, I will do I will list the challenge we have. You can see permitting, coordination, and site preparation. And I will speak about multi-expertise team. One last item is the importance of collaboration, curiosity. When you work on the commissioning of project battery energy storage system, you need electrical, mechanical, software, and automation team. They need to work together and understand each other's constraints. Collaboration, curiosity, clean communication are often what makes the difference between success and delay. And finally, geopolitical context. Today, environment is complex and changing. Trade duties, less funding, or tax credit on renewable, general uncertainty create financial pressure and influence project execution and even project viability. All these challenges are real and clearly significant. But with expertise, experience, strong process, and close cooperation between all parties, including technology provider, customer, supplier, and grid operator, we can deliver grid battery energy storage system, good project, and really good value too. Because the battery energy storage system is the most flexible and versatile energy asset. They can provide energy, capacity, ancillary services, and other services, and you can put the system where you want. Thank you.
Thank you, Sonia. Love your presentation. Thank you. So we have time for just one question if you have. Otherwise, we will move to our second speaker, which is Dr. Marc-Anthony Goulet. He's an assistant professor in the Department of Chemical and Materials Engineering here at Concordia. As the originator of the symmetric cell testing methodology for the flow battery durability, Dr. Goulet is the leading expert in this area and has been integral to the development of the most stable electrolytes currently known. His work have expedited the formation of hardware flow battery spinout, Quino Energy, for which he is currently a scientific advisor. Dr. Marc-Anthony Goulet, please.
Thank you, Mesam. I have a lot of animations in my slides, so hopefully this pointer works. And for those of you on Zoom, I'm afraid you won't see my laser pointer here, but I'll try to describe it as best as I can. My perspective is more the academic perspective on the research, the different technologies involved in large-scale grid energy storage. And so I'll jump right into it because I do have a lot of slides. So I'll start talking about grid electricity storage, the market and the market need. And so here is essentially the projections. This is a fairly old source, but it was a projection of the grid storage demand for storage assets up until 2024. And so the idea is that, as you can see, everything is increasing exponentially, whether it's in power or gigawatts or in energy, gigawatt hours. There's a very large and increasing demand. And so, sorry, I'll go back here. And so Sonia already mentioned some of the market use cases for storage. Here's another graph which shows quite a bit more use cases. And so I want you to maybe focus on what's called CAISO, C-A-I-S-O, so the California Independent System Operator. So they are the grid storage operator that control the electricity in California. And so they have some of the most renewables in their grid, and so they have a lot of need for storage because of the intermittency. And so the idea is that all of these orange lines go towards essentially where do all of those battery or storage assets go, what are the market use cases. So it's difficult to read all the way over there, but the idea is that you have essentially load leveling, peak shaving, energy arbitrage, which is down at the bottom. And that's the one I want you to focus on because that's what I'm going to talk about next. So energy arbitrage means that it's essentially like the stock market where you can, where you can buy and sell electricity instead of funds. And so the idea is that, as a private citizen, you can buy a battery and take that hydroelectricity from Hydro-Quebec when it's cheap, so maybe at 1 p.m., like Mesam was saying, and you can sell it at 6 p.m. when the demand is greater and the price is going to be a little bit higher. And so that is what we call the energy arbitrage market. And from a study at Harvard back in 2017, they did a little bit of economics around it, and what is the cost of a storage asset that would make that kind of idea profitable, right, or break even. And so this is a bit technical, but they called it the break-even overnight install cost in a certain energy market in a day-ahead real-time market. So the idea is that if you are below this curve of kind of blue boxes here, then technically your storage asset is cheap enough such that you can make a profit on this energy arbitrage market. And so the idea, something I want you to focus on here, is that to really enable renewables, intermittent renewables, we need to have 8+ hours of storage available, right? Right now, the overall grid is not 100% renewable, and so we don't necessarily need 8 hours of storage, right? People need maybe 2, 4, 6. But once we get more renewables on that market, we're going to need more, right? The sun goes down for 10 hours, 12 hours at night, and so you need that much storage to really give back to the grid. And so at 8 hours, essentially your storage asset needs to be under this $100 per kilowatt hour line to be profitable. If you really want to enable as many renewables as possible, 100% renewable grid of intermittent solar and wind energy, then you're probably safer going to below $50 per kilowatt hour, right? And so that's the target that was published by the DOE, Department of Energy of the US, a while ago, and that's kind of what we've been focusing on as academics since then. And so really that's our goal in terms of grid electricity storage technologies. And so here I'll get into what are the technologies that are out there. So let's talk about what are the metrics that matter. So something that's very common is this Ragone plot, which shows the power density of the technology versus the energy density of the technology. And here it's in volumetric density, not gravimetric. So it's in watts per liter or per meter cubed, or watt hours or joules per liter or meter cubed, instead of per kilogram or per pound, right? So for battery electric vehicles, the space matters, but the weight also matters. For grid storage technologies, we don't care about the weight generally. We just care about how much space it takes up, right? We don't want to have very, very low density energy storage. We generally want to have higher energy density. And so the idea is that you have, obviously, lithium ion is super well researched. It has evolved quite a bit because of its use case, right? It's not just for grid storage. It evolved for essentially personal portable storage, right? Laptops, cell phones, and all of those conveniences. And so the idea is that it evolved so much because it has theoretically a very good energy density. Some of these other technologies, like capacitors, they have good power density, but you can't actually store much energy in them. Otherwise, you have things like, where are they? Fuel cells, which are kind of a little bit of both. You can have good power density, but you can also have very good energy density because hydrogen is a relatively light and compact source of energy. On the other side, you have PHS down here. PHS, which is pumped hydro storage or pumped stored hydro, and CAES, compressed air energy storage. And you have also flow batteries, a vanadium redox flow battery, which has a relatively low power density and a moderate energy density for now. And so these are some of the things that you automatically look to in research. You kind of set your targets on, okay, what am I going for? Am I going for high energy density or power density, or do I need both for this particular application? So that was for performance metrics, right? How much power and energy can you get in a certain compact form? But really, grid storage is all about cost, because at the end of the day, for that energy arbitrage, you want to have a battery that is, let's say, under $100 per kilowatt hour of an installation cost, meaning the whole package, the batteries, the battery management system, all the secondary containment, everything, all of that needs to cost under under a certain price. And so here is a fairly small or dense graph where they've plotted, and this is from PNNL, Pacific Northwest National Laboratories. So they did a cost study on these different technologies. So you have, let's say, lithium-ion LFP, like the Evlo technology, and you have lithium-ion NMC, so nickel, manganese, cobalt, and you have lead-acid batteries, like you'd have in your old car, right? A lead-acid battery to start your car. You have vanadium redox flow batteries, this is the green X. You have zinc batteries, you have pumped stored hydro, compressed air, gravitational, thermal energy storage, and hydrogen. So all of these are all different types of energy storage technologies, and they all have different kind of cost metrics. And so the idea is that for different sizes of systems, so let's say a 1 megawatt, a 10 megawatt, 100 megawatt, 1,000 or 1 gigawatt, you have essentially different kind of cost values for each of these technologies. Some of them scale better than others. But also within the size, so that the amount of power you need to produce, you can also produce that power for 2, 4, 6, 8, etc. hours, right? And so it's not only about power or energy, it's a little bit of both. And so the idea is that LFP is actually one of the cheaper technologies among all of these for most of these use cases, except once you go down to very, very large installations, 100 megawatts, 1,000 megawatts, then it seems to be more cost effective to have, let's say, pumped stored hydro or compressed air or sometimes thermal, right? Vanadium, the green X vanadium flow batteries are a little bit more expensive, but they also come down in the same way as LFP with duration. And so I'll get into that in a minute, but first I want to just mention that these are not exact values. This was a kind of academic study from PNNL, National Research Lab, and the idea is that it's very difficult to actually get true values for some of these things because there's a lot of competition in these markets. Also, although the original study by Harvard about the CapEx, so the installation cost of a technology, has to be under $100 per kilowatt hour, that's the DOE target, it's actually not the only thing that matters. What really matters is the levelized cost of stored electricity. So not just the initial installation cost, but also how long is that system going to live? How much operating expenditure do you have? Like how much do you have to maintain it? How expensive is it to maintain, right? How quickly does the system kind of crumble? And so that has to be factored in, right? With interest rates, with all of that. And when you do that, you get something called the levelized cost of stored electricity. And the idea is that this is in dollars per kilowatt hour, but it's close to essentially the prices that you pay for electricity with Hydro-Quebec, right? You pay 9 cents per kilowatt hour, 10 cents per kilowatt hour. And so essentially this storage asset, right? The same different technologies, lead acid, lithium ion, and all of that, they all get a little bit closer together when you think about that levelized cost of stored electricity. Okay, and so there are differences, and LFP is still leading at the bottom, but the actual values get a little closer, right? And so really both things matter, right? The upfront cost, right? The amount that the government needs to pay, the government of Ontario wants to pay to install a storage asset. Obviously, they don't necessarily have infinite money. They do have a cap on that installation cost, and that is a factor. But the levelized cost of the electricity is also a factor that they consider when they're thinking long-term. And again, take these values with a little grain of salt, right? This was a kind of academic study, and some people disagree with some of the numbers used in these studies. And so I'll just describe a little bit about what are these technologies. So pumped stored hydroelectricity is essentially Quebec, right? Quebec has a lot of water that is at a relatively high elevation versus the St. Lawrence, right? So all the water flows down to the St. Lawrence, and we collect that electricity or that energy by running turbines from that water flow. And so you can do that artificially, right, if you have an elevation change and a reservoir, a place to put the water. And so you can take a bottom reservoir and say, oh, I'm going to just pump the water uphill, store it at the hill, and then when I need more energy, I'll pump it back, I'll let it flow back down and harvest the energy that way. So that sounds great, but unfortunately, there's actually not so many places that you can do it. It's geographically limited in availability. And the reality is, worldwide, most of this has been tapped, right? Most of these areas have some kind of pumped hydro storage installations on them. So obviously this is one of the cheapest technologies. You just need a pump and then an actual generator, and that's pretty much it. So it's a very attractive option if you can do it. Compressed air energy storage is kind of the same thing, but with it's a mechanical energy storage where you use compressors to compress air and store it in a container, and then you can just let that air expand, and it will turn your turbine or your generator to create electricity when you need it, right? But obviously, creating a reservoir with compressed air is expensive. You need a pressurized tank, and so people have said, well, why don't we just use the earth and these salt caverns, which are relatively not so leaky. You can actually push air into these salt caverns at a very large scale to store a very, very large amount of energy. And that's why this compressed air energy storage it became cost effective at very, very large scale, right? Because you can imagine it's a very large industrial setup. It doesn't really work at small scale. Again, same with pumped hydro. This is obviously it's not available everywhere, right? We don't have so many salt caverns in Quebec. You can't necessarily do it anywhere you want. And so this is also geographically limited. This is more of a new technology, so the space isn't tapped out. There are more salt caverns where this could be done, but it probably won't be enough to satisfy all of our storage needs. Thermal energy storage. This one is a completely thermal technology where essentially you are heating up, you're using electricity to heat up some kind of medium, right? Some kind of liquid or solid, heat it up, keep it isolated, right? Like in a thermos, essentially, right? Keeping your coffee hot in a thermos until you need that energy later. And so then you let that hot material essentially heat up some water into steam, right? You need temperatures above 100 degrees. So you heat up the water into steam, and that steam turns a turbine, and then you collect the energy that way. So in that kind of classical thermal energy storage, you are limited by thermodynamics. Same way that a car engine works, same way that any kind of steam engine works, you're limited by thermodynamics, so the efficiency of this technology isn't so great, right? It's on the order of 50% on that order. Some people are thinking of kind of new ideas around this, which don't involve steam. So this is a technology from MIT that's kind of up and coming, where they are still just heating up a material, blocks of graphite, to very, very high temperatures, 3,000 degrees. They keep them isolated. And then when they want to harvest the energy, instead of water and steam, they instead have these special photovoltaics that harvest these hot photons, essentially, right? The heat is harvested as photons in a photovoltaic. And so it's a direct generation of electricity, so you avoid that thermodynamic limit. So both of these are improving. Both of these technologies, all of these thermal energy storage technologies are improving, and they might become viable options for large-scale power plants in the future. All right, so that was some of the actual technologies, but where are they, right? How developed are they? Are they ready? Because we need these things now. And so what is ready? Well, the reality is batteries are ready, especially lithium ion, because it's been developing since the 90s or even before that, right? They're good. They're very good batteries, and so why not just put them all together as a very large storage asset and store our energy that way? And so that is what is happening. They are the most advanced in TRL, or technology readiness level, right? They're ready to be deployed. They are being deployed. And so that's why they are commercial at this point. Whereas you do have some up-and-coming technologies, right? Like I said, the compressed air energy storage is kind of pilot scale demo, but it's not actually being deployed at, in multiples. Vanadium redox flow batteries here, same thing. They're kind of at the pilot demo scale, but they haven't really been adopted to kind of reproduce the systems in many different locations. So in general, though, because they come in such a small format that is versatile, you can just put them all together. They can accommodate many different system sizes, right? Batteries are the most versatile of these storage assets, and that's another reason why the market is shifting towards them. Now, how strongly is it shifting towards them? Very strongly. So the idea is that here's a graph from IEA, so the International Energy Agency. And so this is 2023 real data of the global installed energy storage capacity by scenario. So gigawatts, so this is in power. So the amount that was installed in 2023 was somewhere around 250 gigawatts, and most of that was pumped hydro, right? Like I said, it's the cheapest, so it's the one people turn to first, right? Cheapest and easiest. It's not difficult. And so behind the meter batteries and utility scale batteries are just a small fraction of this. But because pumped hydro has been tapped out, it's not going to increase in the future. And so the idea is in 2030, we're expecting that utility scale batteries and behind the meter batteries are going to be the bulk of energy storage being deployed. And so to achieve net zero emissions, right, this is actually how many batteries we need, according to this report. So 1,500 gigawatts, or 1.5 terawatts of batteries. How much is that? The total output of Hydro-Quebec, the entire province of Quebec, with all of our magical hydroelectricity, is only 37 gigawatts. So, think about that for a minute. Imagine all of our dams, all of our big reservoirs producing power at its usual rate. We need about 50 times that amount to get to net zero globally. Okay, so it's a pretty serious endeavor. So batteries, that's what I research. So conventional batteries, which is not what I research generally, are kind of the ones you recognize here. So they're kind of cylindrical, or sometimes they're flat like the ones in your laptop. And they're generally constructed kind of like this. They have a cathode and an anode, so two electrodes that are separated by a special separating material. They might have some specialized electrolyte in them. And they're wrapped and they're wound and they're sealed and they're protected by a casing. They have little current collectors. And so the idea is that if you need more energy, right, the energy in these kind of batteries is stored in a solid material, right? If you need more energy, you just need more of that material, right? And so you just need more of these layers, right? So you have to spend the same amount of money to increase the amount of energy, right? So generally, more energy just means more batteries, right? In contrast, flow batteries are a different beast altogether. So they're a little bit more like a car engine or like a fuel cell, where you have a fuel that is separate and it's in a tank, and you send it into an engine and it reacts and gives you the energy. That's how an internal combustion engine works. But a flow battery has a fuel that is rechargeable. So it's liquid, it goes into the battery, which is this electrochemical reactor here in the middle here. And so you send in your liquid electrolytes, you can charge them or discharge them, and they come back into their reservoir. And so overall, you change the state of charge of your liquid electrolytes. And so just like having two electrodes in regular batteries, in this case we have two electrolytes, which we call negalites and posilytes, for negative and positive electrolyte. And so the idea is that because the energy is stored in a liquid electrolyte, if you need more energy, you just need a bigger tank and more liquid. And so that's kind of a simpler technology to a certain extent. And also because of that, if you need a longer duration battery, you just need essentially more of that electrolyte. And so that means that the cost of the technology scales with the cost of the electrolyte. And so the idea is that as you go up in duration, your cost comes down to just the cost of the electrolyte. So as long as the electrolyte is cheap enough, this is a winning technology. And so the most famous one is the vanadium redox flow battery, which I'll just shout out to Maria Skilis-Kazakos, who invented it in 1986. Vanadium is an element of the periodic table. It's got four oxidation states that are available. So essentially, this is the +5 oxidation state, +4, +3, +2. So this one can give electrons to that and become this one, et cetera, right? The more electrons you give these, the more it goes down in oxidation state, and it changes color quite beautifully. So this vanadium flow battery is essentially sending these two electrolytes through the reactor to either change from V4 plus to V5 plus or V3 plus to V2 plus, and in that way you get this storage of energy. Now the key to this technology is that it's the same vanadium, essentially the same element on both sides, both electrolytes. In addition, an element is not, you can't destroy it generally, it won't decompose. And so these electrolytes are very long lasting and recyclable, right? You can reprocess them into another battery later. So it's actually a very recyclable technology. Now, unfortunately, it just happens that vanadium is not quite cheap enough, right? And so here's an example of just the basic cost of the chemicals in batteries, okay? And so here's a lot of different battery chemistries, some of them that you've never heard of, but the idea is that you have lead acid, which is somewhere down here, right? You have lithium cobalt oxide up here, right? You have lithium air here. Vanadium redox flow battery is up here, right? It's above $100 per kilowatt hour, okay? And so that's why it's not, it will never satisfy that intermittent renewable energy kind of our energy arbitrage case. So, among these battery technologies, people are obviously trying to look downwards, right, to cheaper chemical costs. And so, for example, you have iron, which is obviously very cheap, zinc and bromine, sodium and sulfur. But I want to bring your attention to AQDS BR here. So AQDS bromine, which is right around that $100 per kilowatt hour, okay? That's where organic flow batteries come in. And so that's the research that my group does. So I'll just give a little shout out to this. So the idea is that we don't necessarily need to use just mined elements from the periodic table, right? We don't need to just dig up metals from the ground and try to put them in flow batteries or traditional batteries. We can maybe synthesize compounds that have the properties that we want. And so that was an idea that kind of started in the 2013, 2010s. And so the idea is that this molecule here, you can convert this anthraquinone to its hydroxy form, right? So the idea is that you can give it 2 protons and take away 2 electrons, essentially, and give it 2 electrons to reduce it to this anthrohydroquinone here. And so the idea is that this can be done reversibly. You can go back and forth between these 2 states of this molecule, which will be dissolved in a liquid, right? So in aqueous solution or non-aqueous solution. So the real advantage of this is that, you know, this isn't the only molecule that we can design, right? And this is a naturally occurring molecule, but there's many, many other molecules that since 2013 have been tried in flow batteries, okay? And so they all have different potentials, right? So which will give you different voltages in the battery. And, you know, this is just from 2013 to 2016, you had all of these examples in academic research. And then there was more and more and more and more. So now we're just kind of constrained by the imagination and innovativeness of chemists. And so the idea is that we're hoping, right, that we can, you know, go lower than $100 per kilowatt hour, right? AQDS bromine was a battery based on this core molecule with sulfonate groups over here. So this is AQDS itself here in the middle. And the idea is that if you put that on one side of your battery and bromine on the other side, you have that $100 per kilowatt hour target. So some of the real advantages of this is that potentially you have lower cost starting materials, right? You don't need to dig up vanadium or lithium or cobalt, which are very expensive and scarce materials. You can just convert oil or even just take ethanol, right? So bioethanol from natural sources and try to up-convert it and keep transforming it into the molecules that you want with organic chemistry. And so generally, the idea is that we're no longer constrained by scarcity. That's the goal. So generally, these molecules have fast kinetics and slow crossovers. So we're hoping that they actually work for kind of a long-lasting flow battery. Long-lasting is a question, right? Because these are organic molecules, they can decompose, right? And so that is kind of the latest trend in the research, is that people are looking at how to make these molecules last longer. Otherwise, the cost, right? Doing that synthetic chemistry isn't free, right? Making these chemical transformations can be quite costly. Okay, sorry, going over time here. So that's the current challenge. And so I'll skip this slide, very technical, but I will just highlight one last thing, is that we do have one of these new electrolytes was developed recently in Quebec from these 2 great chemists that I collaborate with at Université de Montréal. And so we did have this molecule right here come out last year as a new posolite for flow batteries. And so this is one of the first highly stable posolites for flow batteries, and now we're just looking for negalites. So just to summarize, energy storage capex going below $50 per kilowatt hour is kind of the golden ticket to enabling intermittent renewables on the grid everywhere. Many technologies are available, many storage technologies are available, and there's clear winners at different durations and system sizes. But generally, batteries, right, are the most versatile option that are likely to satisfy the majority of market use cases, okay? And then finally, we do need supportive policies for faster research to reach the goal before the world reaches global warming tipping points. So with that, I thank you very much for your attention.
Very informative, thank you. Unfortunately, we don't have any time for any question. So without further ado, we are going to have our last presentation from Andrew Thiel. Andrew is the Vice President of Policy and Government Relations with Energy Storage Canada. Andrew joined EECS with over 10 years of experience working in the energy and environmental sectors, having previously held roles with Bruce Power and the Ontario Chamber of Commerce and Ontario Government. Andrew, the floor is yours. Thank you.
Awesome. Thank you very much, Mason. I take it my presentation is up. So hopefully everyone can see that. Appreciate the opportunity to appear. Apologies that I am not there in person. I have had quite the daunting travel schedule and actually am headed out of the country in about 24 hours for a number of days to do some business development on behalf of ESC in China. So unfortunately I cannot be with you today. As Mason noted, I'm Andrew Teal, Vice President of Policy and Government Relations with Energy Storage Canada. I've been asked to provide kind of consider the policy perspectives that are driving storage development here in Canada. I will note that I will largely root this presentation in what's happening across the number of jurisdictions in which we operate. And I think that's important to note because when it comes to energy storage at ESC, we approach storage not as an ideology, but as a merit-based solution. Grounded in evidence, system needs, practical outcomes, and we look at the various technologies as my previous presenter just kind of outlaid there, and work with governments across the country to determine how, where, and why storage can benefit their grids based on the current realities that they're facing. It's important to note from a policy perspective that political climates shift. Governments are formed based on different ideologies with unique grid mixes across Canada, and each grid has a unique solution for storage that it would benefit from, and ESC's job fundamentally is to kind of present that on behalf of our members to government and look to drive that policy agenda forward to open up opportunities for procurement for storage technologies. So who is ESC? ESC in and of itself, we are a national trade association. We are a nonprofit, nonpartisan organization founded in 2016. We work across Canada to support the responsible deployment of storage. Today, we represent about 110 members across the country, which includes developers, utilities, Indigenous partners, manufacturers, OEMs, technology providers, and service firms. We are first and foremost technology agnostic. That means that we support the full suite of storage solutions, from short duration lithium ion that was just talked about to long duration pumped hydro or compressed gas, compressed air, and we engage across the entire value chain. Our members are involved in the manufacturing, integration, as well as deployment and operations of these resources across Canada, internationally as well, but again, I'll primarily focus on Canada here today. At its core, ESC exists to ensure that energy storage is understood and positioned with decision makers across all levels of government in order to build a reliable and affordable clean energy future. Just to give folks a sense, of some of the members that we interact with on a daily basis. Evlo is obviously a member of ours as well, not included on the slide, so my apologies. But the purpose here is to show the cross-section of the full energy ecosystem that we represent. Utilities, developers, investors, professional services, all coming together around a shared recognition that energy storage is central to reliability, affordability, and clean growth. Now, as you can probably appreciate, some of our members have differing perspectives on which technology is best suited for where, but the job of ESC is to be an aggregator of opinions, directions, and ideas to inform, decision makers at, again, all levels of government who don't necessarily or are not necessarily energy experts in their own right about the opportunities for storage and how it will enable many of the key policy drivers that their jurisdictions are chasing, that our current federal government is chasing, that Mason outlined obviously with the net zero future that Canada has committed to by 2050, how all of these various technologies will play a critical role in enabling that transition. So, from a policy perspective, as Mason and some others during the previous presentations have pointed out, storage is often looked at as an enabler of renewables. That is certainly a prominent feature of the technology, but what is important is also that storage can do what pair well with other technologies outside of renewables. We like to say that storage is like bacon. It goes well with almost everything. No matter what kind the electricity supply is, energy storage helps the system optimize it. Storage can be deployed or co-located with generation. It can be a standalone grid asset, and its value comes from simply how it strengthens system reliability, increases flexibility, and increases efficiency across systems. With nuclear, storage has historically played a role complementing relatively inflexible baseload generation. In my home province of Ontario, we have about a 60% mix of nuclear resources that make up our grid every day. Historically, a lot of those nuclear baseload assets, specifically overnight, where there was a surplus baseload situation, when paired with storage, it allows us to utilize the resource and electrons from the nuclear resources at a time of day when there is higher demand, again, as Mason pointed out in his first slide. With natural gas, we've seen jurisdictions like Alberta increasingly pair storage with gas resources to primarily improve operational performance, which has reduced cycling, improved ramping capability, and ultimately has lowered emissions intensity while maintaining reliability. Wind and solar, renewables, obviously storage is one of the most direct tools available to firm variable output, maximize transmission utilization, and reduce curtailment, making better use of existing infrastructure. With hydro, storage supports optimized dispatch and more effective use of water resources, especially as demand patterns, as Mason pointed out, become more complex. The main takeaway is storage is not competing with the grid, it is enhancing every part of it regardless of the supply mix. And again, as I mentioned, when it comes to a policy angle, a lot of different governments are inheriting energy systems that were built on decades of energy decisions based on certain ideologies or based on certain availability of technology types. So when it comes to advancing the discussion around storage across Canada, it is paramount that ESC, our members, and the work that my policy team does is grounded not in ideology, but on the system merits and benefits that storage can provide. We looked at some of the international growth projections for storage, but I wanted to again kind of bring this back home and show folks what is currently happening in Canada. So last year, around the middle of the summer, we worked with an energy firm called Power Advisory to do kind of a market outlook, looking at the opportunities for storage as we advance towards that net zero by 2050. As you can see, there is a great number of storage projects underway, planned, committed, or otherwise, or already in service, with more expected to come onto the grid. But what you see on your screen right now is just a small snapshot of where we see things going. In the future, to meet, our net zero policy objectives, we see a potential increase in storage across the country of about 20 to 40 gigawatts, again, depending on how some of those other electricity system decisions are made. But what all of this is pointing to is storage is very much in its early days in terms of development and its understanding in terms of its services to the grid. Obviously, Ontario is kind of leading the way here, but again, a large amount of that is just committed or planned. In-service has just started to take place. In fact, in Ontario, we've procured about 3,000 megawatts of storage in the past 18 months, with more expected in the future through some long lead time, which will largely encapsulate our long duration energy storage technologies, as well as some potential longer duration battery storage technologies as well as we look into the future. Sorry, apologies, my slides are a little bit out of order. I was kind of playing with them as I was sitting here. So again, touching on Canada specifically, and what are the policy drivers and changes that are accelerating the deployment of storage across the country? The fundamental critical element here is that storage tackles, Canada right now is focused on projects of national interest, and connecting new loads like data centers through storage as a critical enabler is at the forefront. As we think about Canada's future economy and grid, one of the most rapid demand drivers that Mason also pointed to is AI and advanced computing. These are not abstract concepts, they are real capacities and real megawatts that will shape our electricity system in the coming decades. On the investment side, the Government of Canada has already signaled strong support for domestic AI computing capacity. The federal government strategy that was released a few months ago committed nearly $700 million specifically to sovereign AI infrastructure. When that is combined with what is expected of follow-on funding and private sector commitments, the targeted investment in AI data center build-out for Canada is north of $2 or $3 billion. At the same time, Canadian institutional capital is moving aggressively into digital infrastructure. And the grid implications are significant. These step loads can add tens or even hundreds of megawatts to single sites. The traditional way we meet demand was through transmission expansion. That's very expensive and time consuming. Can take up to 8 to 10 years for the planning, approval, and build of many of these poles and wires. In contrast, energy storage systems, regardless of type, although again, primarily battery or various other chemistries, as Marc-Andre pointed out, can be permitted and built in 2 to 4 years or less, giving system operators usable capacity far more quickly than waiting for new lines and substations. What this means in practice is that storage doesn't just help us integrate renewables or AI data centers, it creates room for economic opportunity that is already knocking on Canada's door. We talked about that potential AI boom in terms of potential capacity, but there are many other factors obviously driving demand growth right now that Mason pointed out in his slide. Again, electrification, vehicles, electric vehicles, and other things like that. Storage enables all of those things. It allows us to defer or avoid expensive grid upgrades while supporting major industrial and computing investments that will pay dividends for jobs, exports, and obviously Canadian technological leadership. For the federal government, storage is not just a climate enabler, which has largely, driven the conversation since the election of the Trudeau Liberals, circa 2017, but it allows provinces to utilize surplus power, improve reliability, and strengthen regional coordination, as well as expand interties. Without storage, interties often move electricity when it happens to be available, not necessarily when it is needed. Obviously, a huge component right now of the National Projects Office at the federal government is how we can strengthen our east-west as well as north-south interties for provincial reliability, utilizing, again, some of those various grid mixes and technology types that already exist across the country and utilize them in provinces that may not have that flexibility. This is especially important, obviously, when Canada looks to expand its electricity exports and supports its energy superpower agenda. Apologies if I am stealing that language or borrowing that language from the Ontario government here, who is very much, focused on building out Ontario as an energy superpower and leveraging that for Canadian benefit across the country, as well as we look to expand our assets as a means of economic development and job growth. Energy is no longer just, kind of a reliability tool. It is very much looked at across multiple provinces as a driver of economic activity, and that is fundamentally probably the most profound policy metric measure that is determining right now what decisions are made, where, and when. The other piece that I wanted to touch on, and obviously Marc-Andre covered this as well, but I wanted to provide a practical example of some of the declining costs that we're seeing with storage and what is largely driving this accelerated pickup across multiple jurisdictions. So obviously I mentioned Ontario, and it's near 3,000 megawatts of procurement that has happened over the last 18 months. So what we saw actually is from that storage procurement is a very clear and important sign of the trending declining costs of storage. So in May of 2024, Ontario's latest procurement, they secured capacity at an average contract price of $672 per megawatt month, which marked already a 24% cost decrease from the previous round only a year earlier in 2023. So that is a drop from 881 megawatts again to $672 per megawatt month. So clearly, and by comparison to some other resources, storage costs are increasingly competitive with alternatives. For context, some of the gas-fired contracts in similar rounds through the latest procurement processes here in Ontario was around $1,600 per megawatt month. So again, obviously, the declining costs of some of these technologies, their use cases, their understanding, are all shaping how we look at them as a viable and more cost-effective alternative, ultimately at a time when, Canadians are certainly facing an affordability challenge. I won't call it a crisis because I think that's inflammatory, but we are certainly seeing, whether it be the cost of groceries, rent, or otherwise, all across the country, the challenge of affordability is a critical policy driver when it comes to government decision making, and ultimately that translates into energy policy as well. The cost of these resources, how they are built out, who owns and operates them, is a critical driver of decision making. So when we have a technology that is offering solutions in a near-term, more affordable basis, it is certainly something that has to be highlighted from a policy perspective. So, Canada, based on some of the slides I've shown, based on some of the conversations that my fellow presenters showed you, obviously is becoming a leader in battery energy storage deployment and operational expertise. Storage is moving quickly from pilots to large-scale procurements, giving Canada real-world experience in how these systems can support their grids. That expertise is not just valuable domestically, it positions Canada as an opportunity to export our integration know-how, our planning models, our market design, as well as our technology in and of itself. Obviously, think about companies like Evlo, who spoke today as well. At the same time, we're advancing next-generation storage technologies. Companies like Hydrostore and others demonstrate that Canada has the innovation capacity to lead not only in lithium-ion deployment, but also long-duration technologies that have a different use case than your traditional BESS in many energy systems. Furthermore, this creates economic opportunity. Storage presents a credible domestic content pathway across manufacturing, system integration, engineering, and grid services. With the right conditions, Canada can build a supply chain that supports both the near-term and long-term deployment of storage resources through a strong industrial base. I think to the recent opening of the Next Star facility in Windsor, which is going to export, I believe, I'm going to get it wrong, so I'm not going to put the number, but a number of battery cells for LG systems across the US, across Canada, as well as many international partners through the work that is happening there. And that's, thousands of jobs here in Ontario, here in Canada, all through domestic manufacturing of battery cells and battery modules, which, we expect more of that to take place as well. Domestic manufacturing will reinforce deployment, not slow it down. Ensuring that Canada captures the full economic value of these projects that are going to be deployed at a large scale in the next number of years moving forward. So what does that all mean? A couple of takeaways that I would just kind of highlight in terms of my presentation. First, storage. Why is it happening so rapidly? Why is it such a good model for many system planners and governments across the country? It can be deployed on relatively short timelines, and as I pointed out, at a more affordable basis than some other technologies in the past. Second, and something that I didn't touch on but is really critical to highlight as well from a policy perspective, is the opportunities for Indigenous participation, partnership, and ownership that are occurring through these projects. It is becoming increasingly important across all jurisdictions in Canada that Indigenous participation from an equitable standpoint is enabled through energy projects. In Ontario alone, in those 3,000 megawatts of projects that I mentioned, almost all had equitable partnerships from Indigenous participation, which is really carving out an opportunity for some real reconciliation amongst our Indigenous communities, and should not be considered lightly when it comes to future energy planning and energy projects. Storage is really one of those technologies that, based on its relatively moderate capital costs, creates a unique opportunity for Indigenous communities to get involved in these projects and benefit from the local work that is happening across the country. Third, as I already mentioned, it strengthens our imports and exports, and we are certainly facing a favorable market time when it comes to the declining cost of storage. Beyond that, obviously storage will and helps to deliver measurable emissions reductions and local environmental benefits, particularly when it replaces certain types of diesel or other fossil fuel generated resources. So those are just some key highlights that I wanted to put in place. I unfortunately have to run, so I am not available for questions. I have to run to another meeting, but I will quickly flash on the screen my contact information. I am happy to have a conversation with folks if they have questions about ESC, the work that we do, or how they can get involved to help, or just learn more from us. Myself or a member of my policy team would be happy to have a conversation. Mason, I really thank you and Concordia for the opportunity to appear today, and I do apologize that I have to run, but thank you everyone for your time.
So we don't have that much of time, unfortunately. Sonia has to leave too at 12, so I will jump into the panel discussion. And he left? Yes. Okay, so I will just ask some quick question that I have a lot, but unfortunately I'm just going to ask small questions. So I have a particular interest in rural and remote communities. My family is related to rural areas, which are often more vulnerable to power outages, right? Do you see the deployment of larger scale energy storage for rural communities and rural communities and remote areas?
Remote area?
Yeah.
Yes. Sure, in Quebec.
Mm-hmm.
Yes. Oh, yes. Thank you. In Quebec, yes, it's a plan to put more battery energy storage system in remote community to increase the green transition. Yes, and we did that year by year, 1 or 2 projects. And yes, it is in the plan. Yeah.
And how do you see the public acceptance? Do they accept to deploy a new thing that probably they don't know?
Yeah, each project have a challenge for acceptability. Some project have not really problem with that, and other one we need to explain, and that's why Evlo help the developer to explain what is the system, why is the advantage of each system, and normally the acceptability is good.
Okay.
Yeah.
Okay. Happy to hear that. And for the last question,
Yeah.
to respect your time,
Thank you.
as the larger scale energy storage systems become integrated into our grid, power
Yeah.
grid, they can become a critical asset,
Yes.
right? And we really want to know your opinion about the cybersecurity when you're deploying these large scale batteries.
It's really important, the cybersecurity. Evlo mindset, when we think about cybersecurity, we think about that the first day of the design. Okay, each component, BMS, converter, need to have to be cyber safe. Each component, and after that, we put a level of cybersecurity. This is the first thing. The second thing is we have a Canadian EMS, and this is really good for the cybersecurity because it is in Canada, and we develop the EMS. We know it's us. And after that, we work with all customers because each customer have different level of cybersecurity, different requests. If I speak about one USA customer, the customer wants to keep his data in USA. And we develop a USA infrastructure for their data. And it's sure we follow a NERC-CIB standard when we develop the product.
Okay,
Yeah,
thank
really
you.
important.
Just really last question. What do you see? What is the real driver of integration of larger scale energy storage, in your opinion? Is it for renewable energy? Is it for the reliability of our grid? Is it can be the buying less and selling at high prices? What is right now and what it can be in the future?
Yeah, I think it is the demand. Okay, the demand is increasing, and we need energy. We need capacity. This is the first driver, and we need now. And I think I think this notion of time is really important. We can develop a battery energy storage system and solar panel in between 4 years. It's really different if we compare to traditional generator of energy. This is the big advantage of battery energy storage system. And at the same time, I think we need firm commitment for each country about the green transition.
That's right.
This is really important, and it's not only a commitment on in 5 years or 10 years. We need ambitious target annually, and we need to follow that. And we need to publish the result of each country. Because this can influence other one country, the early adapter can influence in good way the other one, the other country. I think it's important.
Thank you. Very
Good.
informative. Just to respect our audience, if you have any question for Sonia, you can ask. Yes, please.
Just a reminder for everyone, if you have a question, raise your hand so that I know I can bring this microphone to you. And for those online, if you have any questions, feel free to pop them into the chat and we'll read them out. I see a question over here.
Thank you for the lovely presentations. Just really quickly, Professor, I didn't see a mention any of kinetic storage. So you talked about battery technology, and you talked about obviously air and hydro. But I'm just wondering if there's any potential in lifting of large built environments to then power or store energy in kinetic energy.
Right. Yeah, I think so. Generally, it's called gravitational energy storage. Yeah. So there are companies working to move big blocks or big sacks of earth, essentially rammed earth, into heights and then bringing them down. So it's kind of the same mechanical sort of energy as pumped hydro storage, but generally all of those things cost a certain amount. And from what I've seen, it only works at larger scale again, right? Yeah, because that kind of initial investment in the crane that brings it up to a higher height or something, or the elevator, whatever they use, that initial cost it needs to be distributed over a very large project, essentially. Yeah.
4 hours of renewable integration plus the larger scale energy storage. Do you think it's a realistic things to think about, or is it necessary, actually?
Well, I think that it depends on the area, right? If there's a place that does not have good solar and also doesn't have good wind, it's going to be really difficult to do it there, right? So think of like the Arctic countries, right, that are really high above and they don't have that much sunlight for very large amounts of the year. So in those cases, it's going to be really difficult, and they're going to need their own kind of base load energy supply, right? So hydropower or nuclear or whatever. But I think for a lot of the world, we do have enough wind and solar to, when paired with storage, to kind of just rely on those intermittent renewables. I think it is possible. And do we need it? Well, again, it comes back to, do we want to avoid global warming or not, right? Yeah.
Yeah. Do you have the same opinion about this? Yeah. Okay. Sure. How do you see the position, the level of importance of the sustainability when we're innovating new batteries, new larger scale energy storage, right? The cost should be low, but that's not the only thing. It should be green, it should be sustainable. How do you see the position of sustainability?
First item I think it's really important is the domestic content. Okay. Presently, when we develop a system, the sales come from China, and there are a lot of boat emission we need to. We have a lot of boat emission come from the transportation, and if we develop the domestic procurement chain, I think this will be helpful to decrease the emission. Yeah.
Also for national security, right?
Yes, too. Yes, too.
I mean, that's a good question, right? Especially in my area, we're doing research for like 20 years down the line.
That's right.
We generally want to think of greener technologies that are going to be more sustainable, right? We don't want to innovate into a new problem where we have extra battery, like dead batteries lying around everywhere that we have to deal with, right? Toxic compounds, et cetera, right? So we want to try to design batteries that are either easily recyclable, right, where we can reuse a lot of the materials, or just batteries that are based on materials like the organic stuff that can kind of be decomposed and is not toxic to the environment, right? Kind of biodegradable to a certain extent.
Yeah, thank you.
Yeah.
Thank you for your answer. And any question from the audience?
We have a question over here.
This is the last one.
Yes, thank you for the presentation. Mark was saying that energy storage cost is going down. Is it because of competition? Is it because of labor, cost? I missed that point. Maybe you could explain it.
Sure, I think actually Sonia has probably a better answer. The cost curve coming down for batteries is due to...
Yes. Yeah, the main reason is the volume. you know, more value, more volume, and more optimization of the production. This is the first reason, and we see too the decrease of the lithium, and this is the second reason why the costs decrease.
Okay, thank you so much for
Thank
your
you for your
presentation. It was
invitation.
really
Thank you.
informative, at least for me. I hope it was for your audience. Thank you, and have a good afternoon.
Thanks, Miss Sam. Thanks, everyone, for coming in. Also, for your questions. We're going to be closing up the Zoom and the live stream now, but this does remain available on our YouTube channel, and you can revisit it there. You can share it. You can also have a wonderful afternoon. Thanks again.